In June 2023, China's National Supercomputing Center in Wuxi posted benchmark results for a machine with no Nvidia chip inside it, and the number it posted sat in the exascale range, meaning roughly 1 quintillion floating-point operations per second, enough to rank among the most powerful computing systems ever documented. The pressure to reach that threshold did not come from the chip Nvidia was barred from selling. It came from the gap that ban opened between the chips China still had. One calculation routed through that gap will show you exactly how. That calculation is a matrix multiplication, the arithmetic atom at the center of every large language model, every image classifier, every system that learns from data at scale. Follow it from the moment it is queued for processing, through the legal wall that closed its first choice home, through the architectural pivot that rerouted it, and you will see something the individual news reports have not quite assembled. The restriction that was meant to sever the supply chain may have soldered the next one. The export control did not stop the compute. It redirected its architecture, and that architecture may outlast the chip it was built to replace. Start with where the calculation was supposed to go. China's national research programs and its largest commercial artificial intelligence laboratories made exascale compute an explicit infrastructure target, not a wish list item, but a named deliverable written into 5-year planning documents and into procurement announcements from supercomputing centers in Wuxi, Tianjin, and Guangzhou. This is confirmed. The government planning documents are public record. The top 500 list entries naming these facilities are on the record. The performance targets are published, so when the calculation that would eventually train a trillion-parameter model was queued, it had a named destination, a machine that did not yet exist but that planners had already committed to building. That commitment is the first link, and it makes every link that follows necessary rather than incidental. The calculation's first choice home was Nvidia's highest-throughput data center accelerators. In October 2022, the United States Commerce Department's Bureau of Industry and Security issued export control rules restricting the sale of those chips to Chinese customers. Successive revisions followed in October 2023, and afterward, each tightening the threshold. The accelerators that defined the frontier at that moment, including the A100, the H100, and their successors, required a license that was not being granted for Chinese customers. This, too, is confirmed. The Federal Register notices are public. Stockpiling of pre-ban inventory occurred. This is reported by Reuters and Bloomberg, but not confirmed in precise quantity, and whatever was stockpiled is finite. The pipeline from the world's dominant accelerator supplier closed. The calculation had a destination and no longer had its preferred route. What happened next is where the chain bends. Chinese supercomputing centers and the domestic chip ecosystem pivoted toward what engineers call a scale-out architecture rather than a scale-up one. Instead of acquiring fewer extremely powerful individual chips, the strategy became bind together many moderately capable domestic accelerators using a high-bandwidth, low-latency custom interconnect fabric, and make the fabric itself carry the performance weight that no single chip could carry alone. The accelerators involved include Huawei's Ascend 910 series, whose published specifications are on record, as well as chips from Cambricon and Byron and custom processors developed specifically for national supercomputing programs. Multiple systems appearing on the top 500 list and related rankings have reported configurations consistent with this topology. This link is graded reported, not confirmed, because full interconnect specifications for the specific national supercomputers remain only partially disclosed, visible through academic papers and procurement documents, but not publicly released in engineering detail. This is the pivot the whole chain depends on. The decision to treat the interconnect fabric as the primary performance lever, rather than the accelerator die, is the single architectural choice that either holds this chain together or breaks it. If that bet had not been made at scale, none of what follows would matter. The fabric choice is where the chain either holds or falls apart, and it is worth sitting with that for a moment before moving forward, because it is not the kind of decision that gets reversed cheaply. Once you have built thousands of nodes around a custom fabric architecture, the fabric is the machine. You are not swapping it out when a better chip arrives. You have made a structural commitment. Think of it the way a relay race works when you change the team. A single world-class sprinter carries the baton the entire distance, fast and without interruption. The scale-out system runs that same distance with a dozen competent runners, each covering their own leg, handing the baton off at every exchange zone. The total time depends less on any one runner's top speed than on whether the handoffs are clean and quick. The export control eliminated the sprinter. China built the exchange zone. That image becomes precise at link 4, and this is where the inversion sits. Because the individual accelerators in a scale-out system are not individually dominant, the system's aggregate throughput depends entirely on whether the fabric can sustain the communication bandwidth that the distributed calculation requires. In distributed training, the critical operation is called all-reduce. Thousands of accelerators must periodically synchronize the gradient updates they have each computed independently, pooling those updates so that every node's model weights reflect what every other node learned. The all-reduce is the handoff. If the fabric is slow, the runners wait at the exchange zone and the whole relay stalls. The reported performance of Chinese exascale-range systems, including configurations based on Huawei's Ascend line and on the Sunway processor family, appears on the available benchmark data to derive its headline figure more from fabric throughput and from the efficiency of the collective communication layer than from per-chip compute density. This inference is drawn from the ratio of reported system-level throughput to published per-chip peak figures for the accelerator families involved. That ratio has a gap in it, a gap large enough that the fabric must be doing significant work to close it. The calculation does not go faster because the chip improved. It goes faster because the path between the chips shortened. This is where the chain's expectation turns over. The performance did not come from the chip everyone tracked. It came from the network that connected the chips no one was watching. The export control targeted the chip, and the targeting hardened the fabric. This link is graded inferred, and that grading matters enormously. The benchmark data exists. The attribution of its performance to the network rather than to raw per-chip throughput is the analyst's inference, not the engineer's public claim. Several analysts covering this space have made that argument from the available figures, but no Chinese supercomputing center has published an engineering breakdown that confirms the attribution. Whether the lesson generalizes, whether the fabric-first architecture is a reproducible blueprint or a one-time demonstration optimized for a specific benchmark run, rests on an inferential foundation, not a disclosed specification. That distinction is the chain's most important asterisk. The calculation arrives, but it costs more to send than it used to. Link 5 is the efficiency toll, and it is reported rather than confirmed, because the data that would nail it down is inconsistently disclosed. Scale out at extreme node counts increases the energy cost of the collective communication operations themselves. Every all-reduce traverses more hops through the fabric. The fabric consumes power. The chips at each node consume power even during the latency windows when they are waiting for the fabric to complete a synchronization. The calculation is not wrong to call this a cost rather than just an engineering detail because power is not an abstraction at this scale. It is a budget line, a physical constraint, and a recurring expense. Reported power consumption figures for Chinese exascale-range systems that have disclosed this data suggest energy efficiency, measured in performance per watt, that trails the leading Nvidia-based clusters by a margin that multiple analysts covering the top 500 and Green 500 rankings have described as material. The exact figures are facility-specific and not always disclosed. The Green 500 rankings, which sort systems by efficiency rather than raw performance, show the gap, but Chinese national supercomputing centers are inconsistent in what they report to that list, which means the gap's precise magnitude is contested. Analyst estimates from firms that track this data span a range wide enough that the shortfall could be large or merely significant. What is not contested is that the scale-out architecture, as currently deployed, does not win on efficiency. The calculation arrives at exascale-range throughput. It does not arrive cheaply. Now for the ground that is softest in this chain. The benchmark data underlying links 3 and 4 is the weakest foundation in the structure. Chinese supercomputing centers do not submit to the same uniform third-party verification that the top 500's LinPack benchmark demands of its entrants. And several of the highest profile claim figures from Chinese national systems have not been independently reproduced by outside teams. The reported performance is what the centers released. What the systems actually sustained over a full training run at production scale, as opposed to a benchmark window, is not public. There is also an unresolved question about whether the custom fabric performance reported in academic papers reflects production-deployed hardware or purpose-built demonstration configurations, a distinction that matters substantially for whether the architecture generalizes beyond the machines that generated the headline numbers. These are not fatal problems for the chain, but they are the places where a skeptical analyst would push first, and they deserve to be named rather than papered over with confident phrasing. The efficiency gap in Link 5 is where the chain's most consequential uncertainty concentrates. If the power cost of the scale-out architecture is structural, baked into the topology rather than tunable by a firmware update or a future chip revision, then China has reached an exascale headline without reaching the sustained frontier training economics that headline implies. A machine that can post an exascale number over a benchmark window and a machine that can sustain a months-long frontier training run at that scale are not the same machine. That distinction, structural efficiency gap versus tunable one, is the open question the chain has not resolved. It is also the question that determines whether the fabric-first architecture is a durable strategic asset or a capable but expensive workaround. Pull back and trace the full chain. China's planners set an exascale target, confirmed in public documents, and that target made frontier accelerators a strategic procurement priority rather than a discretionary purchase. The export controls then confirmed cut off the highest throughput chips available to fill that target. The domestic ecosystem pivoted, reported from available data, to a scale-out architecture in which a custom interconnect fabric bears the performance weight that no single domestic chip can bear alone. The reported performance of the resulting systems appears on the inferred reading of available benchmark ratios to derive its headline figures more from fabric efficiency than from per-chip compute density, which is the chain's structural inversion. The control targeted the chip, and the chip's absence built the fabric. And the power cost of winning that way, reported as material by analysts tracking the efficiency rankings, is the term of the trade that has not been widely priced into the public conversation about whether China's supercomputing programs are closing the gap or redefining where the gap is. The restriction did not prevent the calculation from running. It decided how the calculation ran, and that decision produced an interconnect-first architecture that now exists independently of the chips it was built to compensate for. The fabric outlasts the gap. Nvidia's absence didn't leave a hole in China's supercomputing stack. It left a blueprint. The next cycle will show one of two things. Either the efficiency gap closes as domestic accelerators improve and the fabric becomes a genuine force multiplier, allowing the scale-out architecture to compete not just on peak throughput but on sustained training economics. Or the power cost compounds and the scale-out architecture hits a ceiling that raw node count cannot raise, because the all-reduce operations scale with the number of hops, and hops cost watts, and watts cost money, and at some point the economics of the architecture itself become the constraint. Watch the Green 500 rankings for the Chinese entries. That column, more than the headline floating point operations figure, will tell you which chain you are actually in. If you want to follow that column as the data comes in, subscribe and turn on notifications so you do not miss the update when the next set of rankings lands.